especially in the form of kind of inserting some movies and short videos, long documentaries on the subject of astronomy, but we just don't have time. So this is my little plug that beginning in the fall, I'm going to start teaching it both semesters, Intro to Astronomy. In the fall, I'm going to teach it in the face-to-face setting, and then in the spring, I'm going to teach it in a hybrid format, so I'm kind of excited about that. So keep that in mind. I'm going to dim some lights, just a little bit of lights. So we left off on this slide, and the documentary we watched, which I actually sent a link for the whole documentary, we're not going to watch the end of it, but it talks about stars living their lives, and one of the things we talked about is mass, and you have a question on your test. Your test is made up, yay, ready to give it tomorrow, yay. So there's a question about what drives how a star lives its life, and it's mass. Okay, they actually have different paths, different stages. And so on this HR diagram, you can kind of see the different types of stars. Main sequence, all stars, regardless of mass, start out in the main sequence. Then they leave the main sequence and kind of go up here in the upper right-hand corner, which this is what? Cooler, brighter stars. Because along the, if you're at the top of the y-axis, you're bright. If you're far to the right of the x-axis, you're cool. Okay. White dwarfs, one of my favorite phrases is retired stars, and that's what white dwarfs are. We heard that in the documentary that we watched on Monday. So actually they kind of cool off, and our star is going to end up as a white dwarf. So main sequence stars, the thing that they all have in common is that in main sequence stars, they are basically fusing hydrogen to form helium, converting hydrogen into helium in the main sequence. What do you think this word is? The more massive the star, the blank they burn through their hydrogen. I think it's faster too. Very good. The faster they burn through their hydrogen. So with our sun, we kind of talked about it turned on about 4.5 billion years ago. It's about halfway through fusing its hydrogen that it has to form helium. And then actually, and I think I have a slide coming up. Yep, or not slide, it's what our sun's going to do after it leaves the main sequence on the HR diagram is it's going to be a giant, a red giant. It's swollen, kind of maybe picked up in the video on Monday. And as it swells, it's actually going to go beyond, it's going to consume Mercury and Venus. So 5 billion years. Do you think life will change on Earth when that happens? Yep. So, now when a star leaves the main sequence, again, it depends upon its mass, what it's ultimately going to do from there. Okay, so mass of the original star. So I'm just going to kind of quickly talk through kind of some options. Low mass stars in our, low mass stars, and this is considering our sun, is actually going to be just kind of a brick. Okay, a chunk of carbon actually, kind of. When it talks about 0.4 to 8, that's relative to our sun. So our sun is 1 solar mass, so 0.4 to 8, okay. Red giant, they eventually actually form carbon from fusing helium, and they end as a white dwarf. Okay, so 8 times the mass of our sun is kind of the cutoff. Now, there are definitely stars out there that are more massive than our sun. Okay, if they are more than 8 times the solar mass of our sun, up to 25, they do something different. They actually blow up, and that's the part of the video we were leading up to, and we didn't finish watching it. But the blow up part, you might have heard of this before, let me find my pen, is what an event a star can go through called a supernova. And there's actually 2 types of supernova. This is in supernova type 2, actually. And when it blows up, this one will blow up and leave behind a neutron star. A neutron star is on your test. Okay? A neutron star is kind of the thing that didn't blow up. Okay? Now, If it's more than 25 solar masses, as it was on the main sequence, then it's going to blow up supernova and it's going to leave behind a black hole. So those are your two options after supernova event. Those are both after supernova. And they're both massive stars. But this is even more massive. Black hole. And I have just one slide to talk about black holes. Does not do it justice. I will tell you while I'm talking about black holes, this is only one way to get a black hole. There are other ways to get a black hole. You might have heard of the Hadron Particle Collider. The HLC, is it in France? Okay, but anyway, here on Earth we could create a black hole if we wanted to. It's not good. So, all right, so again, it has to do with mass. So I'm going to kind of talk you through a little bit more about the stages. We talked about main sequence, that's the first stage, and stars live most of their lives on the main sequence. For they're between 0.4 and 8, okay, we said it's going to end as a white dwarf, and you can kind of see it moving on an HR diagram. That figure up here, think of that as an HR diagram, which, by the way, you might want to know how to draw an HR diagram. So you kind of see the main sequence is the white line. You see our sun, perhaps, leaving the main sequence, okay, becoming a giant. Now, I'm going to talk about planetary nebula here in a minute, but planetary nebula is basically kind of near the end of the life of a star, and I'll kind of show some lines here. It's actually kind of sloughing off its material, and I think that the video we watched on Monday talked about a planetary nebula. All that material over the billions of years that the star, not all of it, but the outside material kind of sloughs off, makes these beautiful things called planetary nebula. No joke. Actually, the reason they're called planetary nebula is because people used to mistake them for planets. Okay, so there's a planetary nebula, and they have kind of proper names. I used to think like, oh, Eskimo Nebula. So where's the next Eskimo nebula I can look at? No, that's the proper name of that particular planetary nebula. Okay. So more than 8 solar masses, and it's just, you can't help it. It's a gravity thing that, and a matter thing, and a fusion thing. The thing, it's going to blow up. So this is kind of showing you something greater than 8 solar masses, what that would look like. It starts out normally, lives its life more quickly because it's massive. The interstellar cloud, protostar, high mass star, leaves the main sequence to become a giant, red supergiant, blows up, supernova, leaves behind either a neutron star or a black hole. Okay? This actually is a photograph, and I've tried to get an image of this. This is Messier object number 1. In astronomy, when we start to kind of look at the skies, we catalog them, and the Messier catalog system is one way to catalog them. This is the Crab Nebula, and somewhere in there is a neutron star. Somewhere in there is a neutron star. What is a neutron star? It's kind of the end of its after supernova event. It's, instead of a white dwarf, it's the way a massive star will end its life. Either that or a black hole. Okay. More planetary nebula. This is the Helix Nebula, the Gum Nebula. Go figure. It does kind of look like, sometimes scientists are kind of funny with what they come up with. This is the Butterfly Nebula. Again, in each of these cases, since they're planetary nebula, in each of these cases, this was not a supernova thing. Since they're planetary nebula, in each of these cases, there's a retired star or white dwarf. So I mentioned neutron stars are going to be on your test. Now, you might be like, how do we know there's a neutron star there? Well, first off, neutron stars are the little pit of the star after it's blown up. And I said it's going to be between 8 and 25 solar masses. One thing about it, and I think the video I know talked about how dense a white dwarf is. Well, a neutron star is even more dense. So on your test, since it's so fresh in my mind, it goes something like this. I call it they call it a neutron star. Now, in chemistry, we talked about 3 subatomic particles: neutrons, protons in the nucleus of an atom. Starts with letter E. What's outside? Electrons. Yep. And so here's the deal. At the end of its life, after the supernova event, during the supernova event, the electrons and protons combine to form neutrons. So I call it neutron soup. That's kind of how I phrase it on the test. So neutron soup. It's so dense, okay, that it's even more dense than a white dwarf. Another really cool thing about neutron stars, and we see this in the Crab Nebula, okay, which is what we call a remnant of a supernova event. So one of the things about neutron stars is they spin really fast. You're like, well, what does that have to do with me? They're clear out there, they're spinning, I really don't care. Well, from their poles, is this right? This is actually, the white stick is the axis of rotation of the neutron star, okay? And then this actually, you kind of see the ghosty sort of thing, that's actually an energy field, an electric energy field, and it's sending a beam of particles out. So can you see where the beam of particles is offset by its rotation? And so if that's the case, as it spins, it kind of sends this signal out like this, okay? And if we happen to be in the way, this is Earth, happen to be in the way of the signal, we get a blip, we get a blip, 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 and that's a pulsar, okay? So that's so cool. And actually, when they first started finding these blips, they called them LGM, standing for Little Green Men. See, they're so funny, right? Because they're like, dude, we have little green men, we have aliens trying to contact us. And they're like, then they backtrack and they're like, oh, that's coming from a supernova event. Oh, that's actually the signature of a neutron star. So that's pretty cool. Then the last slide, oops, sorry. So pulsars is the one. Pulsars observed from Earth are not signals from aliens. They're actually signals from neutron stars. This science is just so cool because they keep building. They keep learning more things. All right, so black holes. So I said one way to get a black hole is that if a star more massive than 25 times the mass of our sun goes supernova, the thing that's left behind, what was the center of the star, basically, has become a black hole. Now, the way it became a black hole is basically, we're talking about kind of how dense things are, packed with material. Goodness, a neutron star was so packed that it made the electrons combine with the protons to form neutrons. Well, a black hole actually is so dense, how dense is it? It is so dense that basically the matter now is even weirder than protons, neutrons, electrons. It's just bizarre. The other thing is it has basically collapsed in on itself and taken the fabric of space and time with it. Okay, now, it's confined, and actually I kind of have a slide here to show you how it's confined. Okay, that would be like the anatomy of a black hole. It has what we call an event horizon around it. It's kind of the edge of the black hole. The black hole's in the center. So the deal is if you cross the event horizon, then there's no way that you can do anything other than to basically join the matter that has created the black hole. So you're on your way to basically becoming part of the black hole. So that. But if you're on the outside of the event horizon, you still have a fighting chance of going near the speed of light to have enough speed to get over there. So that's kind of how a black hole works. So that thing in the middle is called singularity. And I mentioned the Large Hadron Collider. So the way that works is a bunch of physicists make a toy, and if this is like the city of, is it Paris? Okay, if this is the city of Paris, they basically have a track around Paris, okay? It's like a big track, okay? And they start at one end, and they use electrical fields to send particles in opposite directions. Okay, so basically what they want to do is get the particle going faster and faster. So it meets over here, and they're on separate paths, so they go faster and faster. They have to give them time to accelerate. It's hard to do. They accelerate, and then at some point, okay, and they have cameras ready, at some point they go ahead and they smash them together. Okay, they smash the particles. That's the Large Hadron Collider. And there's other places that are doing that. Now, why would you want to do that? Well, you'll want to, it's kind of trying to disassemble matter to even smaller pieces. They liken it to, if you want to know how a car worked, you would say maybe take 2 cars, smash them together, and see what parts you got. That's kind of like what they do. But the problem here, and this is what it has to do with black holes, is if you can get matter to basically smash together so much, you can get the density that's required to create the object we call a black hole. Black holes are all about density. They're all about density. All right? Okay, so black hole. Event horizon is your friend. Make note of where the event horizon is. Don't go too close. Okay? I know one of my favorite videos has an astrophysicist talking about black holes are not vacuum cleaners. They're not cosmic vacuum cleaners. They're not like, oh, you know, they're not out to get all matter and suck it in. They just actually kind of mind their own business. If you get too close, you become part of it. So pulsars are an indication of a neutron star, an indication of a black hole, what we call a stellar black hole from a star who went supernova, would be this. Now, way back, just probably on Monday, we maybe talked about that a lot of times stars are born in pairs, 2s or 3s. They actually have what we call a companion. So here's the deal. What you're looking at here is this is a black hole, and it has a live companion, okay? Now, we talked about how our sun is actually going to swell beyond the orbits of Venus even, become a red giant. Well, if a companion star swells, what can happen is some of its outer material can go ahead and be siphoned off onto the companion if it's close enough. And that material then from this star that's alive, it actually then it's like water going down your drain. It kind of forms what we call an accretion disk. And in that accretion disk, there's a lot of bumping and jostling, and actually creates energy in the X-ray region. So that accretion disk makes a signature X-ray signature. So what they do is they look for an invisible dot next to a star that's swollen, and around that dot is an accretion disk. So that's a stellar black hole. Very cool. So these will be due, you can bring a Friday if you want, or you can bring it tomorrow, either way. Yeah, okay? So here's part 6. Good, bad, or otherwise, probably because I was too lazy, but I did not take out any words for part 6. So here you go, just how it is. And I'll try to kind of have fun with it, get you the crux of it, but emphasize maybe what you need to know for your test, since the test is written. All right. Cool. So one of the stories of astronomy I think is so cool is we just take for granted this idea of galaxies. What happened? We take for granted the idea that this planets orbit the sun, and we know that not all astronomers was ever thinking that, you know. But this idea of galaxies actually didn't kind of come till they didn't figure out that what they were looking at was a galaxy until 1921, which seems like just the other day to me. So what they would do is actually, this is a sketch of Lord Rosse, who looked at a galaxy from this telescope. Is that not cool or what? Okay. But didn't call it a galaxy, actually called it a nebula. Okay. Now, if we look at this today, you're probably like, oh, that kind of looks like what I think of maybe the Milky Way galaxy. We don't have the Milky Way galaxy as a spiral galaxy. It looks like a spiral galaxy, and it is. Okay. So not bad. There's a photograph, and there is what he drew. I mentioned the Crab Nebula a minute ago. The blown up star was Messier object number 1. This happens to be Messier object number 51. Okay. So the big thing was after 1922, 1923, and it was a gal, Henrietta Leavitt actually figured out we can look at these galaxies, which now we know are galaxies, and we can see a star kind of flickering off and on, and that can actually, we can get the distance from that special type of star we call a second variable. So once they got the distance to those things, they're like, oh, I think that's not in our solar system, not in our galaxy, that's another galaxy, because of how far they were. I just think that's neat. So one of the things you're going to want to know is kind of this general structure of our Milky Way galaxy. Now, we've never been outside the Milky Way galaxy to take a picture of the Milky Way galaxy, but kind of looking at other galaxies, we think that this is what it would look on, what we say face on. This over here is what our galaxy would look like edge on. I had to do a Snopes search, if you're familiar with Snopes, where you're like, I don't believe that. I had to do a Snopes search because I saw on Facebook, you know, Facebook's all real, right? That one of our spacecraft, NASA spacecraft called Voyager, was leaving the galaxy. I'm like, oh, I didn't know that. So yeah, there was all sorts of comments. I said, I think I said ish to it because I'm like, no. I'm like, those sort of things get out there and you're like, no. While I'm thinking of it, this summer, actually, Mars is going to be relatively close to the Earth in as it orbits the sun, and we're orbiting the sun, so we're kind of like right here. Okay, Earth, Mars, Sun. Now, Mars will not be as big as the moon. You're going to see it on Facebook. Mars is going to be as big as the moon. No. But, so anyway. So yeah, there's what the Milky Way looks like. And so on your test, you're going to want to kind of know a few things about it. Kind of generally its anatomy. There's a Monty Python song out there that one of the lines is 100,000 light years side to side. It's like if you were to look at it face on, that's kind of the width or the diameter of the Milky Way, and that's true. It is about 2,000 light years thick. It has spiral arms, 4 major spiral arms. This one doesn't show it, but we think now that instead of being a regular spiral galaxy, it's what we call a barred spiral. The other thing is it's about halfway, the sun is about halfway from the center to the outside, okay? Another cool thing is that in the center of our galaxy, just kind of like the center in most galaxies, there is a black hole, but it's not just any black hole. That's what we call a supermassive. That's pretty cool term, supermassive black hole. And most galaxies have one. Let's see what else. That'd probably be it. On the sheets I gave you for the sky maps, and this is like one I gave you. So you'll see like kind of a grayish sort of thing there. Okay, that is actually this. That's what we call the Milky Way. And when we look at that, we're looking actually into the plane of our galaxy. So that would be to say that this is above the plane of our galaxy, not our solar system, above the plane of our galaxy, and that's below the plane of our galaxy, or something like that. No, it's not below. But anyway, these are outside the plane of our galaxy. This is into the plane of our galaxy. So if you're looking into the plane of the galaxy, if you have a pair of binoculars, oh my gosh, it's just beautiful. You can see all these little tiny stars in here. So it's just beautiful. So when you're looking at the Milky Way, you're looking kind of in this direction towards the center of our galaxy. And on the previous slide, I think it said the center of our galaxy actually is in the direction of the constellation Sagittarius. So then we actually call that kind of the supermassive black hole in the center Sagittarius A star for that reason. If you look closely, and you can kind of see it in this photograph, you can kind of see dark regions kind of dark regions. And you'll be like, dark regions? Wow, there must not be any stars in the dark regions. And as it turns out, those dark regions are actually kind of gas and dust and cloud that's just not glowing. It's actually sucking in light, these dark regions. So cool, so cool. Okay, I'm doing pretty good for time, I think. So types of galaxies, we can look at some galaxies. This is Messier Object 104. We would call this an edge-on instead of a face-on. You're kind of looking at the edge of it. From the edge of it, you can actually still see the center, what we call the galactic nucleus. Okay, this is a spiral. You couldn't tell it by looking at it. This is also a spiral. But the difference between this and a normal spiral is you see the word barred in front of it. So this is a barred spiral. It's barred because the center actually, the nucleus, is actually kind of elongated and has a pair of major bars coming out from it. And we think that our galaxy is more of a barred spiral than a regular spiral. This is a photograph of elliptical galaxies. Elliptical galaxies, they're kind of blobs. They have no spiral arms and they're kind of, we don't really even have a disk component. Okay, elliptical galaxies. And then the other one is an irregular galaxy. It's kind of a catch-all. It's like miscellaneous. This is on my bucket list. This is the Large Magellanic Cloud. And I've seen images of the sky from Australia. And you can actually, if you leave your shutter open long enough on your camera, you can actually see this. And parabinoculars, you can see it. Parabinoculars from the northern hemisphere, we can see a galaxy called Andromeda galaxy. So, but that one is pretty. So types of galaxies: spirals, barred spirals, ellipticals, and irregulars. I talked about the Hubble Space Telescope here and there. Hubble Space Telescope goes from pole to pole, okay, every about an hour and a half. And this is kind of showing you the Hubble Space Telescope. You can kind of see the solar panels that actually, if you say, oh, I can see the Hubble Space Telescope going across, what you're seeing is a splint from of the sun bouncing off the solar panels. So this figure, or this photograph I'm going to show you, was taken from this part of the Big Dipper. So Big Dipper is a subset of stars, actually, Ursa Major, the Big Bear. The Big Dipper is part of the Big Bear. And what they did when the Hubble went up, after they fixed it, in 93, 94, was to take a part of the sky and we're like, dude, nothing there. There's nothing there. We got the Hubble, let's see what's there. Okay? So this was what it looked like. And if you take this and blow it up, nothing there. It looks like this. So it's a famous picture. It's one of Hubble's earlier pictures. Now, what you're seeing there are not stars. Those are, in general, galaxies. Wow. Beautiful. So, okay, so kind of switching now. We started with our solar system. We've just now finally talked about our galaxy. And now I want to talk a little bit about our universe, how our universe is organized. So this actually is a picture of, see, are there dots there? They look like dots. Those dots represent galaxies. Those are kind of how the galaxies are hanging out in our neck of the woods. Galaxies, as it turns out, are organized into clusters. And I'm like, it's like they had a kindergartner come up with some of these names. Guess what? Clusters are organized into superclusters. Really, no kidding. So galaxies are in clusters, and clusters of galaxies are organized into superclusters. It gets even better. So, like, our Milky Way galaxy is a part of a cluster of galaxies called the local group, or the local cluster. And I think we're part of the super local cluster. Anyway. I mentioned Andromeda that we can see from our hemisphere, northern hemisphere. No need to travel. A pair of binoculars will get you this. And actually, the sky map that let's see what's on here. It's Messier Object number 31. I always look for the W. Have you ever seen a W in the nighttime sky? There's a W. That's called Cassiopeia. Yep. And if you can find, actually, there's Cassiopeia. See the W? W? Near the north? Yeah, I don't think I'm on this spot. Oh, no. Anyway, you can see it through binoculars. It actually has a companion, two companion galaxies, little galaxies. Andromeda is about 2.5 billion. BLY stands for billions of light years away. Billion light years away. 2.5 billion light years away. And of course, Andromeda is a part of our cluster of galaxies. There's a crazy story about Andromeda, and if you see it on Facebook, this one is true. So this galaxy actually is on an intersection with the Milky Way galaxy, which are similar in size. They're both spirals. Andromeda a little bit bigger. And I've heard I've listened or watched documentaries that talk kind of about the merger. It's going to be a long time. I'm trying to think if the sun will even be if we're within 5 billion years. Maybe. So when they intersect, as they get closer, our nighttime sky is going to become a little different. Okay? No collisions with regard to our solar system and our planets is expected, but maybe some cool things will happen. This then is each of these yellow dots represents a galaxy, a cluster of galaxies. So this is now mapping what we would say, mapping the universe. How are the galaxies distributed in our universe? It ends up being actually kind of the galaxies, and it's hard to pick up from here, but the galaxies are kind of organized around large voids. Well, they call them voids, where there's nothing. It's like a sci-fi movie, doesn't it? This is space between galaxies. As it turns out, actually, dark matter is important on the scale of our galaxy, and if you read about it more, dark matter is important on the scale of how galaxies are distributed in our universe. Dark matter. What the heck? I used to try to say a more stronger word. What's dark matter? Well, dark matter basically is stuff you can't see, but you know it's there. And you're like, well, how do you know it's there? Well, how do you know anything's there? I mean, like, I'm trying to think of a good example. You just see its influence, okay? You see its gravitational influence on other things, basically, dark matter. So, in that light, actually, we have, no pun intended, we have dark matter actually surrounding our galaxy. It just is. It just has to be there. This is a picture kind of showing you about the dark matter that's kind of strewn around those little, it's not a photograph, it's a figure. Dark matter kind of strewn between those galaxies that are clustered together. How do we know that? Well, again, I call it dancing. We can kind of see the galaxies kind of interacting with each other, dancing. You're like, oh, there must be something there that we can't see. And it has a certain mass, and it's dark matter. This kind of goes back to, you kind of see the voids. Void, 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 void. And so those kind of filaments, those aren't stars. Think of those as actually galaxies kind of distributed in the universe. It is pretty darn cool. So there is a test question. I think it's a multiple choice question, and it asks you for a question about when did our universe begin. Now, outside of class, especially with the topic of astronomy and all in science, I'd be glad to kind of talk to you a little more about the whole, my faith, quite frankly, where I'm coming from. But 3.5 billion years ago, our universe basically went from singularity. Now, we saw what a singularity was. Singularity was the same thing we talked about in the middle of the black hole. Basically went from being a singularity to the universe unfolded and created two things. Two things we take for granted. Space, you're like, oh yeah, I'm walking around this room, I can go to the door, I can go outside. Space and time. At the point of the Big Bang, it created both of those things. And Einstein, a very bright person, and things have been proven, Einstein said that those two things are intertwined. And oh my gosh, that hurts my brain. I'm like, space and time. So you could have all sorts of sci-fi movies out of that. So about 13.5 billion years ago was the initiation of our universe. So at the time, point singularity, and that has all of the space and the time, the matter and the energy that's going to create the universe, our universe. I personally think of, a lot of scientists do about this multiple universe theory. I'm kind of maybe fond of that. But as it rushed in all directions, it then cooled down, as things do. And so what you're going to see here in a minute on this one figure I'm going to talk about with the creation of our universe, it's definitely cooling and expanding and cooling and expanding. So it took a long time, thus the 13.5 billion years after the initiation of our universe, in order for you figure stars had to be formed, galaxies had to be formed, planets around those stars had to be formed. Okay, all the while, matter is cooling and expanding. So one of the main things that we see that supports this overall theory, remember what theories are, they're not a guess, it's not a hypothesis, it's a theory, is the idea of the Doppler shift. Like, what about the Doppler shift? Well, remember we get a blue Doppler shift for things, we get a red Doppler shift for things going away and a blue Doppler shift for things coming towards us. Red means it's kind of elongating the wavelengths. Blue means it's shortening. It's kind of, remember, like if you have a car that's coming towards you, it goes, that's the Doppler shift. It cranks up, shorter wavelength, and then gets longer wavelength away. So what we see with regard to going away is we see a red shift in the galaxies. A red shift. All right. So this is, I know I said 13, did I say 13.5 in the previous slide, and here's 13.7. I think your test I went with 13.7, so hopefully it'll jump out at you. 13.5, 13.7. So what you're looking at here, this would be your singularity over here, okay? And this is where we are today. This cute little spacecraft called, I can't remember what WMAP stands for, but this one is actually gathering data. I think it's in the infrared region of energies to understand our universe more, to understand what happened. Now, if you go ahead and study the Big Bang, which then people say, well, it was neither big because it was really small, nor was it loud because in order to have a sound, we kind of think we talk about physics, you need to have a medium, so it was actually creating a medium to go. Okay. But anyway, the very beginning, I mean, you're talking a fraction of a second. So 0.00000 with 32 zeros, 1 seconds after the Big Bang. There's a little, we know a lot, but a lot happened within even the first second. If you keep studying, it's not on your test or anything, actually there was a lag time between the Big Bang and 38,000 years. We can't see any farther than that because it wasn't cool enough for the electrons to settle down and associate with protons and the neutrons. It was just too fuzzy. Okay, but about 38,000 years ago, we could actually things settle down so we could see. So you figure it expands, it cools down. At some point, we go ahead and we have matter coming together. So you can get your first stars. The first stars are humongous. Okay? And if they're humongous, they live their lives very quickly, and they did. And as they die, they blow up. Since they're humongous, they have supernova events. And as they blow up, we have all sorts of interesting things happening with regard to chemistry. Heavy metals form. But the other thing is that they can leave their stuff for new stars to be formed. Stars to be formed. Stars to be formed. Okay. So today, these days, okay, the universe is still expanding, but it's not expanding at a constant rate. We talked about acceleration back in physics. Okay, acceleration means not a constant rate, but it's going faster and faster and faster and faster. So sometimes people call, I've heard documentaries talk about the big chill. Because as things expand, they cool down. So maybe our universe is coming to a big chill. Dark matter, dark energy. We didn't talk about dark energy, but dark energy, like dark matter, you don't necessarily know its source, but you can see its influence. So if you were to take our universe and break it up into energy and matter, which is kind of weird, but actually Einstein, I'll put this one up on the board. Einstein says E for energy, you can actually go back and forth between energy and M for mass of the matter. You can go back and forth between these two things. And that's used, I won't say all the time, but that is used all the time. And C is equal to mc squared. C here is the speed of light. What I was going to say is notice that only 5% is normal matter. Okay. So I think this is the last slide. I kind of end up talking a little bit about the acceleration of the expanding universe. So the universe has been expanding ever since 13.7, 13.5 billion years ago. And it's getting larger quicker and quicker. This one actually, and I'm old enough to remember this, back in, what had it been, 1970s maybe? They thought either big chill or big crunch. And so this is the big crunch. So what you're looking at here, this is the Big Bang, okay? Expanding universe, okay? And what they're saying is we have so much dark matter that basically our universe is going to come back together like a rubber band. Okay? So this would be the big crunch. And as it turns out, we don't have that much dark matter. So that one's out. It's not going to be a recollapsing universe. This one is a coasting universe. Okay? You can kind of see that basically we expanded and then we kind of just keep with the same size. That's not going to happen either. Again, the matter of our universe is not right. This one, that's critical universe. This one's coasting. Now, I'm going to show you the last one. The last one is the real deal. So if you compare the third with the fourth one, the third one is expanding, but the fourth one is accelerating. It's a subtle difference. And as it turns out, and for something this big to put before the public, let alone your peers, it's not just whimsical, okay? There is all sorts of different ways of looking at our universe and the data to support this. Okay, but this is what's happening. Okay. This actually, again, if you watch documentaries, it would say that if you take that to like people or a table, table's less gross. Okay, if our universe is expanding, that means the fabric of space and time is expanding. Let's just take the fabric of space is expanding. That means that the atoms that make up the molecules that make up this table are getting farther and farther apart. And it's true. It's true. But what does that look like in 100 billion years? I don't know. I won't have to worry about it, but I don't know. It's interesting. Blows my mind. A lot of things blow my mind. But anyway, hopefully that'll get you ready. Remember, there's a review video out there. Let me know if you have any questions about it. But we'll hopefully see you in here mañana.